In Chapter 12, we'll be looking at alkanes, and what we see here is an image of fields where there might be methane given off as a gas. And methane is a greenhouse gas that's made from the decomposition of organic matter by soil bacteria. Our simplest definition of an alkane are hydrocarbons that have only carbon-carbon and carbon-hydrogen single bonds. These can also be referred to as saturated alkanes or saturated hydrocarbons. Acyclic alkanes are compounds with chains of carbon atoms but no rings. And they usually have the molecular formula CnH2n plus 2, where n equals the number of carbons. So for a compound that has 2 carbons, the number of hydrogens will be 2n plus 2, or 4 plus 2 is 6. So that's how you can use that formula. A cycloalkane has carbons that are joined in one or more rings. The formula of these is usually CnH2n. For a ring with 4 carbons, we're going to have 8 hydrogens in them. So the different compounds we see here, there is a carbon chain here. This one is our alkane that is saturated. It's also acyclic, and this is undecane, so there's 11 carbons there. It's actually a pheromone, which is a chemical substance used for communication in a specific animal species. So these pheromones are used in animal species, often in insects, and this undecane is secreted by a cockroach, which causes other members of the species to get together. And then we have the structure here. This is cyclohexane. There's 6 carbons in that ring, and this is one component of mango. Alkanes that are acyclic are tetrahedral. The compound that we have here is 1 carbon, which is called methane. This is tetrahedral, which we've discussed before. When we draw a tetrahedral compound, there's 2 components in the plane. We have 1 wedge, 1 dash, and it has that 109.5 degree bond angle. So you can see the ball and stick models there along the sides. We have ethane next, which has 2 carbons. And this can be drawn also in the 3D. We have 2 components in the plane, 1 wedged, 1 dashed. And then we have propane, which is 3 carbons. And all of these have 2 atoms in the plane, 1 wedged, 1 dash. Okay, the skeletal structure for propane is just the 3, it looks like a V, but you have 1, 2, 3 carbon atoms. And propane is the principal alkane or component of LPG, which is liquefied petroleum gas. And that's the fuel that's used for vehicles and a lot of times cooking. Some people have LPG in their houses. It's also used as an aerosol propellant, which replaces the ozone-depleting chlorofluorocarbons. Carbon skeletons can be drawn in different ways, but they represent the same molecule. We can draw propane as the 3 carbons in a row, which you can see in the middle there in red. Or it can be 3 carbons with a bend, so those can rotate around. So we just took this whole chunk here and just flipped it down. And there's the 3 different ways of drawing the propane below. So it can be with the point coming up, the point is down like the part of an arrow. You can have it to the side or have it to the other side. These all represent propane. And sometimes these are called conformational isomers. So all we're doing is changing the conformation of the compound. So it would be like taking your arm and sticking it out. That would be one conformation. If you bent your elbow one way, that would be another conformation. But we haven't changed the makeup of your arm. Butane can be arranged two different ways. You can have all 4 carbons in a row, and when we write the skeletal structure, it looks like that. So this is 1, 2, 3, 4. We can also have a constitutional isomer of butane. So the formula is C4H10, and there's one way where all the carbons are in a row, but we can also have branching, where there's 3 carbons in a row here, and there's 1 CH3 sticking up off of that. So when we draw the skeletal structure, I'm going to draw my 3 carbons first. So the 1, 2, 3, and then 1 methyl group is coming up off of there. These are the skeletal structure. So when you have a constitutional isomer, that is defined as something with the same formula but different connectivity. If we look at this robot guy, this is how we would see a standard robot where there's a head, a body, 2 arms, and 2 legs. But if we disconnected the different parts of the robot and put it together differently, that is going to be a constitutional isomer. So if we look at ethanol, it has a CH3, CH2, and OH, where the functional group here is an alcohol. Your total formula is C2H6O. And then I'm going to rearrange this. We take an oxygen, and instead of putting it on the end, it's now sandwiched between the 2 carbons, making it an ether. Our formula, though, is still C2H6O. And the only way we can get to the constitutional isomer is by taking it apart and putting it back together differently. So if we look at this pair of compounds down here, I have a CH3, CH2, CH. So I'm going to add up the formula here. So this is C3H8. And this one has 3 carbons. There's a double bond here, so I have 1, 2, 3, plus 3 is H6. These are not isomers because their formulas are different. And our definition of a constitutional isomer is that they have the same formula, but they are connected differently. This one does not have the same formula. If I look at this compound now with the nitrogen, I add up my atoms. I have C3H9N. This is C3H, there's 3, 6, 9, N. So these are put together differently. In the first compound, I have all the carbons in a row and the nitrogen at the end. And in the second compound, the nitrogen is sandwiched between all of the carbons. So the formula is the same and it's connected differently. So these are isomers. All right, so here we're asked to figure out if each pair is a constitutional isomer or are they not constitutional isomers of each other. The easiest thing to do is to determine the molecular formula. So we have C4H10. This is C3H8. So this is no. Okay, so in this first one I have C6. There's 6 in the ring. And each of those carbons is bonded to 2 other carbons. So there's 2 hydrogens on each carbon, which makes that H12. Here I have 5 around the ring, plus another carbon, so that's C6. H would be 2, 4, 6, 8, 9, plus 3 is 12. So these are constitutional isomers of each other. One is a 6-membered ring and one is a 5-membered ring, but they both have the same formula. As you increase your number of carbons, the number of possible isomers also increases. So with pentane, this is the straight version. This is unbranched. We can also draw CH3. This is 2-methylbutane. So this one actually has a 4-carbon chain and then 1 group coming off of that. We can also draw a structure where there's a carbon in the middle and 4 methyl groups. And these are all isomers of pentane. So this one is 2,2-dimethyl propane. And if you're drawing this skeleton, there's 3 in the main. There's 3 carbons here. And then you can draw the 2 methyl groups branching off of that center one. For this practice problem, we can draw 2 isomers with the molecular formula C6H14 that have 5 carbon atoms in the longest chain and 1 carbon branch coming off of the chain. So C6H14, 1, 2, 3, 4, 5. And I can put a branch coming off of the second one. So if I add up, I'm going to make sure I have 6 carbons. So 5, 6. H is 3, 6, 9, 10, 11, 12, 13, 14. Okay, so we wanted another one with 5 carbon chain and a branch coming off of there. So that's the CH3. So those are 2 different isomers. It has the molecular formula C6H14 with 5 carbon atoms in the longest chain and 1 carbon coming off of the chain. If you were to draw this one, these 2 are the same. They both have the 5 carbon long chain with the methyl group coming off of the second carbon. They're just coming from different sides, so those are the same compound. But with the middle one, that CH3 is coming off of the center carbon. Which of the following is not another representation for 2-methylbutane? So if we draw this out, butane has 4 carbons in the longest chain, and it's going to have 1 CH3 coming off of the second carbon. So this is 1. This is a representation. This has 4 carbons in the longest chain and a CH3 on the second. So this one has a CH2CH, and then there's 2 CH3 groups coming off of that last one. So this is also correct. This one almost looks like it's a ring structure, but if I count the carbons around here, 1, 2, 3, 4, 5, there's no branches here. It actually, if you draw it in the skeletal form, just looks like this. So this one is a no. Carbons in alkanes can be classified depending on how many other carbons it's attached to. So the blue carbons are the carbons that we're looking at, and however many carbons attached to is how it can be classified. So that first one there is attached to 1 other carbon, so this makes it a primary carbon. The next one is attached to 2 others. This is secondary. For 3 carbons, it's tertiary. And for 4, it's quaternary. And if we look at an example in a long chain here, this one here is primary because it's bonded to 1 other carbon. This one is secondary. It's bonded to 2 other carbons on either side. This one here is tertiary because of the CH3 up top and the 2 adjacent to it. And this one here is quaternary. So you can see them in the stick figure structure here. It's the same thing. So this is quaternary, tertiary, secondary, and then the primary one there. So if we're going to look at the example that is drawn here and determine what each of the carbons are, anytime you have a CH3, those are going to be primary. And then this one on the end is primary. CH2s are secondary. And then where you have a carbon with no hydrogens, this is quaternary. So we can continue classifying the different carbons here as primary, secondary, tertiary, or quaternary. Our CH3s are always primary. CH2s are secondary. Primary, primary. CH2 is secondary. Every once in a while you get a CH with 3 carbon groups. That's tertiary. So this one here is tertiary. CH2 is secondary. When we have these alkane compounds, rotation can occur. So one of the carbons can just turn on the other one, kind of like you can turn your wrist or rotate it. So the location of the two labeled hydrogens here is showing how it can rotate. So in the first figure, the red H is on top, and then you can rotate it so that it's across from the blue hydrogen. So rotation can occur anywhere in the compound. Okay, so if you draw pentane, and we draw different ways to rotate it, we can draw the 5 carbons in a row. There's a zigzag form, which we can see there, or you can rotate it this way. That's still the same thing. You can draw it this way. And all we're doing is rotating the bonds around, or you can draw it in a V shape. So all of these are the same thing, they're just rotated around each other. So this is like your elbow bending, your wrist and your elbow bending, as opposed to your arms sticking straight out. It's just being rotated. On this slide, we're asked to determine which two representations are the same and which are just isomers of the other two representations. And one of the ways that you can do this is to count the number of carbons in the longest chain. So this one has 7, with one CH3 group coming off of 3. That one is the same. Okay, so just these two are the same. The last one has the CH3 group coming off of 4. So the first two are identical. The last one is just another isomer. Aside from just drawing a whole bunch of different isomers from each other and counting out carbons, we can use the name of the compound to determine if something is an isomer or not. There used to be names of compounds that just came from whoever invented it or wherever it came from. The odor of garlic is called allicin, and that may have come from the Latin name for garlic. And then this structure is barbituric acid, and it was named for somebody named Barbara, but nobody knows what the root of that is. So there was a group of chemists that got together from the International Union of Pure and Applied Chemistry, and they came up with the IUPAC system of nomenclature. So drug names can be very long and complex. Most drugs actually have 3 names. They have a systematic name, which is the IUPAC name. They have a generic name, which is the internationally approved name for the drug, and also a trade name. And the trade name for a drug is assigned by the company that manufactures it. And this is usually a catchy name that's easy to remember. So for this particular compound, the systematic name is quite long, and then the generic name is ibuprofen, but the trade name is Motrin or Advil. When we're naming compounds, the parent name indicates the number of carbons in the longest continuous chain, or the molecule. The suffix tells us what type of functional group is present, and the prefix tells us the identity, the location, and number of substituents that are present. So this is kind of the graphical representation of the name. You have the prefix, we have a parent, and then we have the suffix. So this might be the parent. This is the parent. This would be part of the prefix. This is prefix also. And then different names will have different combinations of those. So the parent is derived from the number of carbons in the structure. For straight chain alkanes, if the parent has only 1 carbon, that will be called methane. And you're going to notice that all of these end in the ane ending, indicating that they're all alkanes or have carbon-carbon single bonds. And the beginning prefix part tells us how many carbons there are. So for 1 carbons, we'll see the meth. For 2 carbons, it's ethane. And that precursor there is eth. 3 carbons is propane. 4 is butane. So propane is our gas in our homes, butane's in the lighters. Pentane is 5. 6 is hexane. 7 is heptane. So now it's starting to sound like our geometry. 8 is octane. 9 is nonane, and 10 is decane, like a decagon or a decade. So those all have ane endings to indicate that they're carbon-carbon single bonds, and the different prefixes tell us how many carbons there are in the structure. An alkyl group is a group that comes off of our main parent chain. So in the example that we can see below here, you have one CH3 group coming off of there. It's one carbon, so that would make it a methyl group. So we just took off the ane ending and ended it with YL. For 2 carbons, it's ethyl, which is right here. For a 3 carbon chain that's coming off, this is propyl. A 4 carbon alkane chain before was butane. We dropped the ane ending and use YL, so this is a butyl, which is what we see here. 5 will be a pentyl, and 6 will be hexyl. So those use those same precursor beginnings. So meth, eth, prop, but, pent, and hex. When we go to actually name the compound, we have a couple of different rules. The first is to find the parent carbon chain and then add the suffix to that. So we're going to name using the parent with a number of carbons. So if it has 6 carbons in the longest chain, 6 has the hex prefix. Hexane will be the parent for all of these. There's different groups that come off of there, but we're just looking for the longest carbon chain without it branching. So the longest continuous chain. Okay, so that's all highlighted in the gray, and we've numbered those carbons so we can see what the longest carbon chain is for all of them. The next rule is to number the atoms in the carbon chain to give us the first substituent the lowest number. So if you numbered from left to right, we have 1, 2, this is 3, 6. So our parent is going to be hexane. I have a branch coming off at 2. This is my substituent, and that is a methyl. Okay, so this is the parent, which is the hexane, and then I have the CH3 methyl group there. Okay, then we name and number these substituents, and we're going to name them as alkyl groups and use the numbers from step 2 to designate where they are. So each substituent is going to need its own number here. In this chain in gray, we have 3, 4, 5, 6. So the parent is hexane because there's 6 carbons. I have a group, a methyl here at C2. That's at C2, and a methyl at C3. So when I list this, I have 2 of the same group, so I'm going to use di as the prefix. And each one gets a number, so it would be 2, 3 for where they are, and this is dimethyl. Those will be my substituents. Okay, then we combine all of the substituents with the numbers and the parent plus the suffix. We're going to alphabetize the substituents, and we're going to use the methyl and ethyl and that kind of thing to alphabetize, not using any prefixes like di, and then number substituents before naming. Each substituent gets 1 number, and then we're going to separate those by commas and separate numbers from letters by dashes. Okay, so we can see kind of what we started there. Our 6 carbon chain, the parent is hexane. This one would be 2-methyl, because that's where the methyl group is, and then hexane. We look at the next one. Hexane is also the parent here. The 2 CH3 groups, there's one at C2 and one at C3. We have to give each of them a number for each substituent. There's 2 methyls. This will become 2,3-dimethylhexane. To find this name, we're going to look for the longest carbon chain, and it's not always one that goes left to right, so we want to be careful of that. Okay, so that's 8 across. 1, 2, 3, 4, 5, 6, 7. If I go up on the CH2, CH3, that will be 7. So ours is all the way across, and then I want to double check the numbering. The numbering that is in blue gives our first substituent at 2. If I look at the numbering in red, the first substituent is at 3. So I'm going to number it using the blue. At C2 then, this is a CH3, so this is a methyl group. At 6, there's also a methyl group. And up here is an ethyl group. So I have a 4-ethyl, and then there'll be 2,6-dimethyl. My parent is octane for 8. And between ethyl and methyl, I'm going to list them alphabetically, not using the precursor. So I'm going to use the M and the E. Ethyl comes before methyl, so this will be 4-ethyl, 2,6-dimethyl octane. Okay, our longest chain is here. That's 9 carbons. This is 4, and this would be 4 if I numbered backwards. So I'm going to go from left to right here. 1 carbon is methyl. This has 1, 2, 3 carbons. The prefix for 3 is prop, so this will be a propyl group. Methyl comes before P alphabetically, so this will be 4-methyl. 5-propyl nonane. The numbering for the second one, if I just went left to right in the middle here, is going to be 4 carbons. If I started at this CH3 group here, it would be 5. But if I start here, that would be 6. So that's going to be my longest carbon chain here. And my numbering will give a substituent at 3 if I have it numbered the way it is. But if I start on the other side, the substituent in the other direction will be a substituent at 2. So I'm going to use this numbering. I have 2 methyl groups at 2 and 4, so this will be 2,4-dimethyl hexane. And for the next one, my parent carbon chain is here. And remember, it has to be continuous, so you don't count the branches in your carbon chain. So that's the longest. I'm going to number this way, which gives the substituent on the second carbon. This is an ethyl group. I have methyl. And these two are methyl groups as well. So there's a methyl at 3, 2, 5. That will be trimethyl. And ethyl's going to come before that, and that is at 4. And there's 7 carbons, so this is heptane. Our longest carbon chain looks like it might go from right to left. That would be 7 carbons. But if I count the carbons this way, there's actually 8 there. 8, so my parent is octane. And I have 2 carbons coming off here at carbon 4, so this is 4-ethyl octane.